Yeah, it's kind of hard to guess where you're about to go. And when do you think you'll get those homeworks back to us? Give me an idea.
We will. I don't expect to get them back before quiz 1. So they're usually graded in like roughly a week. So I can't. So I won't completely control that, but usually it's roughly a week. And then they'll be posted on. Scores will be posted on Canvas. And so hopefully there's information there. If it's not clear what's going on there, let me know and we can try and correct it. So other thing is the first quiz is going to be in 1 week. That will be in class. The quizzes are in class. It's not the entire lecture. It will be the last half an hour of the lecture. Okay, so at 3:50, that means I will hand the quizzes out. You will take them on paper. You will hand them back in. There will be, I imagine there'll be some of you who will finish, on the order of like 5 to 10 minutes, and there are some of you who will take the whole time. All of this is fine. Usually, it's fine to finish in 5 minutes. It's fine if you want to double and triple check all the things. We can talk more about what's going to be on the quiz on Wednesday. Also, you're allowed to bring in 1 sheet of paper just with just writing on one side of it with anything you want on a piece of paper. In past, otherwise, people print out the entire book of material, and it's it flatters me that you're printing it out, but it's a lot of trees. So just 1 sheet of paper, it helps you kind of to study for the quiz. Great to try and condense what we've learned so far into 1 sheet of paper. It's a good studying. So it's a good way to study for that as well. The quiz will cover up to what has been covered. Probably, let's say, in general, it's up to what's covered in class, up to when the quiz is given. So it could be that lecture. Although we're starting a new lecture on that day, so it'll be, I won't ask anything about the linear algebra stuff we talked about that day in class. But the quizzes and the homeworks are not aligned 1-to-1. Okay, so it'll cover the material covered in the homework, but also the stuff, in the next 2 lectures as well. Okay, there are, I think, 4 quizzes and 5 homeworks, so it does not exactly. Remember, you get to drop the lowest of either a quiz or a homework. Great. So any other kind of administrative questions before we start? Okay, so today we're talking about the central limit theorem. All right, so I will spend the lecture trying to explain this theorem, and maybe you saw this in your probability class if you've taken one so far. Hopefully you saw it, and so I'll try and give my view on what's going on, which is probably a little bit different than how you saw it, and start some implications of it, how it's used in data analysis. Like Bayes' rule, this is one of the fundamental kind of things coming out of statistics and probability, which will be very useful in this. Instead of Bayes analysis, which lets you think about models in terms of data, this will tell you about the concentration of data. As you get more and more data, you should get a better and better estimate of your model. And the central limit theorem is basically kind of an encapsulation of what this mechanism is doing. And so we'll have 2 lectures roughly on this topic. The first one will mainly be just explaining it, what's going on, and then the second one will mainly be kind of showing how to use it in ways specifically towards data analysis, ways which are quantifiable in a way that are consistent with the way more of a computer scientist thinks than how a statistician thinks about it. Okay, so probably there are many ways you can state this theorem. It's actually a collection of maybe 50 theorems that are roughly saying the same thing. And we'll focus on the versions that are most applicable to analyzing the kind of computer science and data science problems we'll be talking about in this class. Okay, so it'll take me a while to get to the actual theorem, but we'll start now with a data set. I'll call this, for now we'll call this P, P1, P2, up to Pn. Okay, so we're going to have these data points, and so kind of if you remember how when we talked about Bayes' rule, we had random variables for the data with random variables for the model, but we're saying essentially the probability of a model. So given the data is really what we are focused on, and Bayes' rule allowed us to twist this around, probably the data given the model, but in the one we're after, the model is the only random variable. We didn't know the data was given to us, so it's effectively fixed. And that's the case here. And so what we're going to assume is that each of these data points is going to be, I'll introduce some notation here, which is very important, is going to be drawn from a probability distribution. So this is a probability distribution function. This is a PDF. So it's a probability distribution function, like a normal function, or it could be a uniform function. It could be anything, but this is a PDF. This means it's drawn from this function. That means it's a realization. P of I is a realization from this function. Okay, so we have, so before we had dealt with just these random variables, which were these kind of variables which were kind of the hypothetical outcome of some process. When we have data, we're actually assuming it comes from some process, and we might not know what this is. Okay, but when we realize the data, when we draw it from this distribution, that's what this symbol is saying. Right, so this is a draw from a distribution. Then it means we're actually realizing this data. This is well, so I jumped ahead of myself here a little bit. So it's going to come from this distribution, but there's going to be something intermediate here. This is a probability distribution. There's going to be a random variable, and then this is going to be drawn from this distribution. What I first want to focus on is that, in general, I'm going to say that, it's right here, that this data set P is going to come from this distribution IID. Okay, and so this will be it's a common phrase to explain what's going on here. I'm drawing n data points, gives me a set P, and they're coming IID from this distribution. When I was in undergrad and a grad student, I heard this term, and for a long time I didn't know what it actually meant. Google has gotten better, but it's hard to look this up on Google. Because often you couldn't find it in textbooks. People use this, and I didn't know what this stood for. Okay, so how many people know what IID stands for, and how many people don't? Okay, good. You're all in the same shoes I was. Or almost all of you, except for a couple of you. So it means, let me get the right order of the I's, but so identically and independent distributed. Okay, so I'm assuming the data, and this is common in almost all data analysis, that the data is IID from this distribution. That means I'm drawing n data points here, P1, P2 up to Pn. They're all drawn from the same distribution. They're all identical. They're drawn from the identical distribution. Okay, so they're all coming from the same distribution, and they're all independent of each other. Okay, and IID here. Okay, and so the identical and the independent are both important. The independence was, as we saw the last couple lectures, was super important for being able to analyze the probability, because we could write down the probability of each term and then take the product of these. Because of the property of independence, you can write a joint distribution as the product of the individual distributions. Okay, and we'll need that in some of the bounds we'll write down on Wednesday as well, that they need to be assumed independence. This is for effectively a different reason of analysis, we'll see. The identical is important because our goal is going to be to learn F, or learn something about F, this distribution here. Okay, we'd like to learn something about F, and if they're all drawn from different distributions, then I can't kind of piece them together to all say something about F here. If they all come from the same distribution F, then I can try and understand something about F by looking at all this data, because they're all talking about the same thing. Okay, so this is what IID stands for. And so I'm going to assume that PI is drawn from F here, but that the set is IID. Okay, so what are examples of data drawn IID? Okay, so there are a few places where this is going to come up, and this is important. So one place that's kind of in the it's like in the news a lot nowadays, is we would like this to come up in polls, right? So if you see in looking at politics, they're trying to say who's most likely to win the Democratic nomination. So ultimately people vote, and so how they try and estimate if who's more likely to win is they will try and randomly sample, say, n equals roughly 1,000 people from the population, ask them so how they're going to vote. And these are, if each kind of person is drawn independently from the population, then these polls, the polls here are supposed to be IID, right? So we're trying to understand one big population, which is kind of like this F model here. It's like a really big number, and essentially it looks like some unknown distribution, and we sample it by getting these realizations, these actual poll. Every phone call where someone responds is one of the data points in the poll. Okay, so if you know anything about how the polling actually works, that's not how they actually run polls. It used to be that they did stuff so this is a little bit of a lie. They have to do a lot to fix this assumption. All the analysis that you do is assume it's IID, but it turns out it's not. For a long time, almost all the polls were done by calling like landlines. So how many of you actually have a landline that you actually answer? Okay, so right. So I have one in my office, but I don't have one at home. Right, so I guess they could call my office, but I think they're trying to call houses, not offices. Right, so landlines don't work as a sample of the population anymore. So some polls are done including cell phones, but not everyone has a cell phone. A lot of people won't pick up their cell phone; they only use it for text messages and such. And more are done on using the internet in various ways. And so what they have to do is they'll try and contact people, and then they'll try and correct it to make it look like it was IID. And there's a whole bunch of magic under the rug here, but in principle, a poll is supposed to be an ID sample. Yeah.
So since you're basically getting the data from 2 different means, one by cell phone and one by the internet, that means that they're not ID?
Right. So like most polls are either cell phone and landline based, or they're just on the internet. Right. There's surveys online where what they might do is they'll serve ads based on could be Facebook or Instagram or just web pages you're doing, and some fraction of people, a very small fraction, click on an ad, and then the people who click on it will ask to fill out a survey. I'm sure how often you actually fill out the survey. It's a small fraction of people, but they do enough of these that they get some data, right? And when they but even with, let's say they just ask the internet stuff goes into the much more complicated things that will beyond the semester, but let's just think about the cell phone and the landlines, right? Let's say roughly everyone has one phone number, or one phone number they could be reached at, okay? And so let's say I call those numbers at random just in the area code that was associated with like Utah. So like I don't know how many area codes there are in Utah, maybe 5 or 6. So they would call all the numbers in there. Maybe they get a record of these. But for instance, I have a cell phone, but I got the number when I lived out of state. So now it has an area code that's not in the state of Utah. So they might not call me unless my phone number shows up someplace else. So they need to try and kind of weight the people who do have in-state cell phones, who they do actually call, who change their number to represent all people who change their number in some ways like that, right? So there are all these ways where it's sampling from the wrong population. But is it IID? Well, some people have 2 cell phone numbers. Some people don't have cell phone numbers. They probably, as I mentioned before, they probably don't call people twice. They probably, so it probably is not truly independent because it's negatively dependent in that way. But that ends up not being so much of an issue. But there's these subtle issues they try and correct for, but all the analysis we'll talk about will be under this assumption.
Isn't I guess you could say like F just kind of whatever you decide to be. So like if you want to use your example of like only calling landlines, then you could make you could do some sort of like analysis on people, but it would only apply to people who have landlines, right? But as long as you don't apply it to everybody, then it's okay. So it's just kind of just like how you want to bin these people. That makes sense?
Yeah. So kind of what they'll do is they'll say they're like 16 different F that they actually care about. They'll start the phone call by quick informational questions. That will put you into one of the different F. And then they have some assumptions on how these are weighted within the population. There are so many people from out of state. There are so many registered Republicans or registered Democrats. And so they'll put you into a bin. They'll learn each of these distributions, and then they'll average them together. Something like this. Yeah. Okay, so but let's just think that we have one of these, and we're drawing from it. Okay, so that's kind of one place it comes up, and it's kind of a tricky example. So like another example is like like sampling animals. Okay, so there's this cool exhibit at the Natural History Museum tracking these herds of elk that go through Yellowstone, and they kind of randomly will capture a few of the animals in each herd, and they'll put a collar on those animals, and then they'll track those animals around as a representation of the entire herd. Right, so let's say they do this by finding the entire herd, getting some sharpshooters, tranquilized, darting kind of a random sample of them by picking out a few, and those that have been tranquilized they put on the collars, and then they're up and join the herd again. right? So they can pick them, in theory, randomly from the herd, right? And this represents the whole group of animals in this way. Okay, and there are other ways you can collect data randomly. You can do a controlled experiment. I can grow inside of a greenhouse like 1,000 different plants, and I number them ahead of time, and then I draw a random sample out of that to kind of actually, I want to know the chemical compounds, so I take them out and I grind them up or something like that. But I don't want to kill everything, right? So I can do that. I can actually control the randomness in a situation like that. Okay, and then a third category. I want to start by saying, well, I want to mention something else about polls. It's kind of sampling a human population. For actual polls in politics, this is hard. If you're an internet company, you're like Adobe, the Adobe group down the valley, or Google or Facebook, they want to sample their users. They can do this exactly random. They can say, they'll do these A/B tests where they take off every time someone logs into Facebook, there'll be like a 1/10 of 1% chance they'll send them and run some demo on them. And they can completely control the randomness in this case, right? So they can get a poll of the population, see how they react to a new version of the website or something like that, and it can be a complete IAD random sample of their users, except for the negative dependency shit. So in internet companies, they've been able to do very precise sort of polling of their customer base. And this allowed them to do some very kind of well-modeled experiments where actual political polls is much more messy. Okay, so the third area are these randomized algorithms. Okay, and we're going to think about these. You can think about random. So how many people have written or used a randomized algorithm? Like that they've interacted close, and so what example of randomized algorithms you've used, or you've written code for? Probably all taken 2420. I know there's at least one.
I don't remember what it's called, but there's one where you take them on, you pick some large number and then another number that's relatively prime, and then you keep multiplying one by an index and then plot it out by the other.
So there's like some factoring algorithms like this. So if you want to factor a large number,
It's a pseudo-random. But
okay.
Yeah, it'll give you random numbers.
Yeah, so actually random numbers in the computer are actually almost always so pseudo-random, but for the point of this class, we'll assume that you can every time you need a random number, you look at variation in the processor speed, and you use that to generate it. That's really slow, but you could effectively do that. Yeah. So any other? There's probably at least one you took in 2420. That one of the basic.
Just as a question, you don't need a number generator.
Not a random number generator, no. Just an algorithm that uses randomness inside of it.
Okay.
Yeah.
So like, would an example be where you take the current time, and set that as a seed for a randomizer?
Sure. So that's one of the mechanisms you might do to kind of use a pseudorandom number so you can't. So it's different every time, but that's not the actual algorithm that you're doing. So I haven't heard from you yet.
RSA encryption.
Okay, so sure, yeah. So RSA encryption. You can do RSA encryption with some randomness. You can make this. I think this can be deterministic as well, though it does not. I don't think this is. I don't think this is fundamentally randomized, but okay, over there.
I tutored a genomics class a little while ago using Python, and all of those use a lot of stochastic algorithms, where it takes a probability distribution and says, okay, this gene sequence is going to converge to this, given all these random inputs.
Sure. Well, let's think of something simpler. What's one of the most fundamental questions?
Monte Carlo simulation.
Sure. Let's here.
Like a hash table hashing function.
Hash tables. Okay, great, great. So hash tables. I'll write hash tables down. So hash tables are like a data structure, which is great. That allows you to kind of store and look stuff up in roughly constant time, but you have to have random access into the table. And so there, you're using random bits to determine the probability of two things colliding in the hash table. It's a little bit more difficult to state what I'm going to describe from this.
Maybe like a primality tester?
Sure, yeah, so there's these breakthroughs in testing if numbers are prime, and it uses randomization within these algorithms. One simple example you probably did in class, probably, so the variation you probably use of quicksort, there probably was a random version of it, right? You pick a random number and you split the numbers to the left or the right based on the random number. You can take the median, but it's often slower to take the median than just to pull a random number in order to do the split. Okay, and so the idea is the runtime of quicksort, for instance, is going to depend on the random numbers you pick as the splits. Okay, and this randomness is, hopefully, this is different every time. Maybe because you took the time on the clock to generate your random seed of a random sequence of a pseudo-random sequence, or you looked at the variation of the processor speed. But the runtime of this is different every time. Well, let's say I'm given a fixed input, right? I can be given a fixed input to the algorithm, so a very big list of unsorted numbers, and I want to know how long is quicksort going to take to run. That's going to be different every time I run it, if I run it by taking a random split. Right? If the pivot is random every time, then the runtime is going to be different every time I do this. But if it's uniform over all of the possible pivots, then the samples I use there are going to be is going to be IID for on the first pivot, I think. Okay, and so that's going to affect the runtime here. And so the runtime of quicksort once is going to give me a value pi, and if I run it n different times with different randomness, different starting numbers to seed it, I'm going to get n different runtimes. Okay? So these are actual realizations. This is my data, and there's some random process, either because it's an algorithm which uses randomness inside of it, and so that affects the runtime, or this could be the runtime here, or maybe the expected numbers, the number of collisions that I have in the hash table. All these will be affected by this randomness, and I can track that as the data. In here, the randomness affects the actual outcome because there's the true distribution, and I'm trying to learn that. Here, the true distribution is a distribution of the runtimes over all the random choices. Okay, so what I was trying to draw here before, and I kind of skipped the gun a little bit, is that I'm going to have this unknown distribution. Okay, so now each and each run of this distribution, I'm going to have these IID random variables, where x is going to be this. Okay, so these are now so now each run of the algorithm I haven't run the algorithm yet, but I'm thinking about running it n different times, 100 times. Each run is a random variable, where I'm collecting some animal from the herd. Each collection or each robocall, whatever, is before I run it, is a random variable of what the outcome is going to be. Okay, and I'm going to collect a set of these IID. Okay, when I actually do the collection, I'm going to get this set P. This is my actual data. Okay, once I get the data, it's fixed. Once I run the algorithm, once I collect the animal samples or the plant samples, or I actually do the poll, I have actual data, right? And then I'm going to analyze this data by doing an average. Okay, I'm going to somehow aggregate this together to do some average, and I'm going to use this average to analyze here. So I want to understand this unknown distribution that's going on. What is the expected runtime of a randomized algorithm? What is the expected percentage of people who are going to vote for vote for Biden in Democratic in the caucuses? I guess the caucuses are messy. So in the polls in so like in New Hampshire, and kind of what fraction of the animals are going to be sick or something like that. Right, I can estimate that based on the average, okay? And so there's this pipeline where I want to learn about the distribution. I'm going to mathematically work through random variables, which we learned about in the probability section. And there's a set of these random variables. But then I actually only see this data. So my analysis is on the random variables. I see the data, and I'm going to take an average here. Okay, so what I would like to do is I'd like to look at the expected value of xi, where xi is drawn from f of x. Okay, so f is this unknown distribution for random variable x. I want to draw any random variable. It doesn't matter which one. They're all identical. And I want to analyze the expected value. And I'm going to do this by taking data and looking at the average. Okay? And so this is a very, very common process, right, where I have some unknown phenomenon I want to understand. I have the data. I take an average. But to write down a central limit theorem, which will be our main tool for this analysis, we need to think about this set of random variables. Okay, so this notation is kind of a, there's kind of a some things going on here. Just to be clear, I'll write p bar is equal 1 over the size of the set. And then it could be some function of pi, but for simplicity, we'll just write pi. Okay, just some scalar values. Okay? All right, so now what the central limit theorem says this central limit theorem is basically going to be, I'm going to have n IID random variables, x1, x2, up to xn, where each xi is drawn from some unknown distribution f. So f is any fixed distribution with the mean of x of f is equal to mu, and it has bounded variance sigma squared. Okay, so I'm going to have n ID random variables x1 through xn, right? So I'm reasoning about these random variables before I see the data. They're each drawn from any fixed distribution. The these have to be, so this is IID here. They're drawn IID from this, IID random variables, right? They're all from the same fixed distribution. It's not changing over time or anything funny like that. And I'm going to write it down in terms of the mean of the distribution and the mean of the PDF, as we define the expected value of any of these variables. This is equal to, okay, and the bounded variance of these random variables drawn from this distribution needs to be bounded. Okay, then, so x bar okay, so I'm going to look at this x bar. An important thing is, so x bar is going to be essentially the average of these random variables. This is, again, a single random variable. Okay, it's a random variable that corresponds with this distribution now, p bar, with this data value, p bar, which is the accumulation of those. Okay, this converges to the normal distribution with mean mu and the variance is going to be sigma squared over n. All right. Okay, so I'm going to have this set of n random variables. They're all drawn identically and independently from f. So it's fixed. That means they're all identical. They're independent, and so that means they're drawn independently of each other. This will be even more useful later. And I know something, and I'm going to know something about the original distribution. It has mean mu, and it has variance sigma squared. And this variance, there's some situations where the variance is unbounded. In this case, it's bounded here. So it can't be infinite. There's some weird cases like that. And then I can talk about the average of these random variables. Okay, and there are 2 points, there are kind of 3 points here, which are important. The first point is that it converges to the normal distribution. Okay, I didn't say anything about what this distribution f was, but when I take a bunch of average of random variables drawn from it, it's going to converge to the normal distribution, this Gaussian distribution, which allows to derive the sum of squared errors and all that stuff. It's going to converge towards that distribution, right? So the average will look like the normal distribution. It's the bell curve and stuff like this. Okay, 2. Okay, so the mean stays the same, right? This is pretty intuitive, but the mean of an individual variable is the same as the mean of the average of the variables. This is a simple consequence of the linearity of expectation, right? I wanted the expected value of x bar, and I can factor out this coefficient, and I can factor out the sum, and then this term is constant for all of them. Okay, this is hopefully pretty intuitive. I'm not changing the mean by averaging. And then the third thing, okay, is that the variance is shrinking. Okay, and it's shrinking at a rate that I can understand. It's shrinking at a rate of 1 over n. So as I get more and more data points, the amount of variance is decreasing. The concentration is becoming more concentrated, right? So I might start with right? So it could be that f is going to be, say, a distribution that's uniform between 1 and 3. So the initial distribution looks like this. It's height 1/2. So if I integrate 1/2 from here to here, it's going to be integrated to 1, 0 outside here. Okay, and then I'm going to draw points from this distribution. Right, and I'm going to take their average of these points, and the points are going to be more concentrated. The average of these points will look something more like this, that looks kind of like a Gaussian. Okay, it won't exactly be a Gaussian. It won't exactly be a normal distribution. There are a few ways why it can't be a normal distribution. The normal distribution has infinite supports, right? So, you know, it has the normal distribution has some probability of the average being 4, and I know that can't happen. Okay, but it will start to look more and more like this. And as it gets narrower and narrower, let's say I've run this for a long time, right? And so I've run this for a long time, and the distribution the normal distribution shoots way up here, you know, and it comes back down. Well, the fact that it wasn't exactly 0 outside of 3 becomes less and less of a problem because the normal distribution was already pretty small, even at 2.5, right? So that becomes less and less of an issue as I take more and more points. Okay, and the variance is shrinking. So that means that, you know, the variance is, again, as I mentioned before, the variance is a little bit harder to kind of conceptualize what's going on. What makes a little bit more sense is the standard deviation, right, of, let's say, of x bar. This is going to equal to sigma over square root. Okay, so the standard deviation is roughly kind of as this distance, or you know, roughly about halfway up the distance from the middle to the edge of the normal distribution. This value is in the same units as the data and the mean, and this one is shrinking at a rate of square root n. So that means to shrink it by a factor of 10, I need 100 samples. To shrink it by a factor of 100, I need 10,000 samples, right? So the poles will often see sample sizes of roughly 1,000, and then the air, though, supports some air number that will be around 2 or 3% is usually what they report. And that corresponds with roughly the standard deviation here. There, all the values are, say, between 0 and 1, and this goes into the calculations in some ways. But usually don't trust a poll unless it has at least 1,000 people. That's usually more than the margin that you care about, unless it's 1,000 or 5,000 people. Okay, so this is a really cool and really important theorem. Now, I've not stated it precisely. I haven't said what converges means here. And this is because in order to state it precisely, I have to define converges, and there are like at least a dozen definitions of what it means to converge. And this is tricky. And so in statistics, there are a variety of ways that they'll define what it means to converge. And there are a bunch of theorems where you make different assumptions on f, right? The most basic assumptions that you need is that you know what the mean is, because then you want to say the mean is stable, right? And the variance is bounded. There are some distributions which are really flat, and the variance becomes basically infinite, and then you can't really say something like this is not well defined, and you can't really say much about this anymore either. So you have to have bounded variance. But if you say assume this is a binary random variable between 0 and 1, which is a common case, or a uniform random variable, or a Gaussian random variable, you can say more specific stuff about this. And you can define converges in different ways other than the mean and the variance that are more precise. Say that the exact maximum height difference anywhere between two distributions is an example. And then you can actually write down kind of how far that is as a number of samples more precisely than just mention these two statistics about the distribution. Okay, so we're not going to talk about any of the kind of the common ones you'll see in a classical statistics course. We'll talk about a number that you will see in data analysis that you can also actually say something like, okay, I have a randomized algorithm and I want this much accuracy on the runtime of quicksort, or I get better and better accuracy on my polls the more samples I do. How many samples do I need to get this level of error? Right, so I can derive and I can do calculus to tell me how many samples do I need to run for, right? And so we're gonna focus on these. Okay, but before I do this, I want to this is kind of an important concept, and maybe it's not clear. And there's this demo I want to show you. So give the lights. Okay, great. That is two. Oh, okay, good so far. All right, so let's look at this. This is some Jupyter Notebook online. You've all seen something like this. All right, so let's just run through this. I need random, and so I'm going to do plotting. So I've defined this function. Oh, this is probably too small, huh? I was probably too much on top, but okay. Is this a good size? Okay, so I've defined this function, plot distribution, and this is going to just plot a histogram, and I'll show you an example. And I'm gonna draw stuff between values 0 and 100, and I'm going to have 50 bins in a histogram. I'm going to count how many things falls in each of the bins here. I'm going to do 1,000 trials. Okay, and so then this is uniform sample. This will give me a uniform random number between 0 and max bin here. So I'm defining this distribution. Yes, I'm renaming this. Okay, and then to plot this distribution, what's going on here? Connecting up with, I may not be on the internet. Great, so I'm not connected online. Yes. Okay, let's. While this is loading, any kind of general questions about central limit theorem? So, how many of you saw central limit theorem in your probability class? Okay, but some of you not seen this before? Is this being covered? Okay, so you guys have generally seen this before, so good. Okay, so I tried to do a live demo, and that's okay. Great. Okay, let's see if this. Okay, so I should be online. Great. Yeah, I should have run this locally.
Try to like restart and run kernel or something, like kernel. Sometimes like restart kernel.
Oh. Okay, well, I'm going to go through. I'm not patient enough. Let me find the book and just go through the example in the. So I've kind of shown this demo in the book. So hopefully you can do it on your own. Okay, so what's in there? All right, so here's what's so here's what's going on. We are drawing. Okay, so I'm drawing distributions from a uniform distribution between 0 and 100. Okay, and I'm saying each time I'm going to draw some and average them, it's going to look like a normal distribution. So this is what happens where I took 2 points from here and I plot their average. So I put 2 points in the uniform distribution and I plot their average as a point, and then I built a histogram. If I just do this once, you know, I get 1 p bar. I get a single p bar here. Okay, and when I see it, it's only going to be one data point. Maybe I do it once and it's 20. I do another time it's 62, right? But if I do this 1,000 times and I plot 1,000 p bars, then it's going to look like this distribution to give a sense of what the distribution for p bars. Okay, this is when I average 2 points. This is when I average 3. You can see it's more concentrated. This is when I'm averaging 10 points, and this is when you're averaging 30 points. Every time I'm averaging here, averaging 30 points, and I'm doing this 1,000 times. Right, so I have 30 averages. I'm plotting all of them, and so you can see it's becoming much more concentrated. Here I've got 170 of the 1,000 points are basically within, you know, within 2 of the 0 of value 50 where it should be, right? Whereas if I average 10 of them, I get roughly 100. If I average 3 of them, I get roughly 60 at the same spot, right? So they're getting much more and more concentrated the more things I average together.
So, sorry, just want to make sure I'm catching it correctly.
Yeah, great.
So in the first one, when you're saying we're averaging 2, you're not talking about just 2 points. You're averaging 2, like you're getting like a collection of points, and you're taking the average between two collections. Is that?
No, so I'm going to be. Yeah, one of the reasons I wanted to step through the Python notebook is you can see what's happening. I can put that back up, but I'm creating a p bar. So let's look at the middle plot with n equals 3. Okay, I'm doing p bar where little n here is 3. I'm creating one value of this, and let's say this gives me a value of 55. Okay, that is kind of one data point here. Now, what you're seeing in the plot is the accumulation of 1,000 of those data points. I run the same experiment where I get a p-bar 1,000 different times. So effectively, I'm generating 3,000 points. And in groupings of 3 consecutive points, I take their average and I plot that. So I get 3,000, I get 1,000 different averages of 3 points. Does that make sense?
I think so. So to get the actual p-bar though, we have to go over all the 1,000 points.
No, p-bar is 3 points.
Okay, p-bars.
This is, yeah, this is the p-bar for 1 point, for 2 points, for 3 points, for 10, for 30 points.
Oh, okay.
Now I'm plotting, I want to show you the distribution of p-bar, of x-bar, right? So x-bar is what's really interesting here. This is the average of the random variable. So I want to show you the distribution of x-bar, right? The original distribution of x here is just the uniform distribution. But x-bar changes as n increases. And it's continuous. I can't, I could probably, for the uniform case, I could probably work out a closed form and plot it, but I'm showing you kind of a sample estimate of the distribution for x-bar. Right? This is also a random variable. It has a PDF, and I'm showing you a sample estimate of the PDF. Yeah.
So every time you do like an iteration, you're choosing different points from the
Yeah. So there are, this plot by itself has 1,000 data points. Each data point is one of these processes. So I put a for loop around this. Right, so let's say, let me go back over to my IPython notebook here. And so what I'm doing is that I've got this for loop right here that runs for 1,000 times. Every time I get one data point, inside the for loop, I'm creating an average here. Right, where I start with 0, I append n things. This could be three times through here. So in 3 times through here, I create a random sample, I add it to my average, and then I divide through by the sum. Okay, so each one of these is one instance of this process to get a p-bar. And then I wrap that in 1,000 different trials, and I plot it. Right? So that's what's, so it's a little confusing because, you know, there's with this plot which we saw before, but like I can't like I can probably work it out, but I can't write down directly a sample from x bar. I know that it looks kind of like a normal distribution. I know the right mean and I know its variance. Right, because I know what the variance of a uniform distribution is basically 2, or I guess the standard deviation is 2 divided by 6 or something like that. But so I can write down the variance of it, but I don't know exactly how much it looks like a normal. Right, this picture kind of looks like a normal distribution. Right, you had I plotted, or Benway plotted a normal distribution for you earlier in the semester, and it kind of looks like this, but not exactly, right? And you know, it can never go outside of 0, and it's in the middle, it's doing something a little bit different. And this is a sample estimate of it. And because it's a sample estimate of it, it's not perfect either. There's some weird stuff going on here, right? So it's not exactly a normal distribution, but you can see it looks kind of like a normal distribution. It started with uniform, right? So if you go, and arguably, as n gets larger, even though it gets more concentrated, arguably it looks more and more like a normal distribution. This looks kind of like a triangle. I believe the exact distribution of this one is going to be, let me move this lower on the screen. Right, so for this, the exact distribution should actually be a triangle distribution like this. Okay, which is an approximation of a normal, but not a very good one, right? And then this one will look a little bit more like it, but not exactly the normal distribution. Yeah.
So I'm guessing for the part where we repeat 1,000 times, if we were to repeat that more times, all it's going to do is just give us a more well-defined curve, basically.
Yeah, so the 1,000 is estimating the actual, is giving a sample estimate of the true distribution, which is not a normal, but is converging towards it. Right, so there are two sources of errors here. One is it's not exactly normal distribution, and two is I have a sample estimate of 1,000. If I could get the IPython notebook running, I could ramp that up to 10,000 or 100,000. You'd see these converge to something.
Like the means of each of these, like sample mean distributions, should still converge to the mean of the uniform distribution if we did it like on paper, right?
Yes, that's right. Yeah, so they all should have a mean of 50, and the sample estimate should converge something close to it. Okay, so great. So let me put this away and talk a little bit more about how to quantify how close we are in a way that will be like a little bit more like a little bit more concrete. So we can't say something. Well, I'm going to avoid talking about how close the entire distribution is here, because this turns out not to be too important. Okay, so it turns out that if the true distribution should be a normal distribution, right? And I'm getting either, and I'm approximating the distribution, and it looks, say, more like this instead, right? So this is the distribution I get. Well, I could measure like this difference, or I can integrate the difference, and there are a variety of ways. Integrate the squared difference. There are a variety of ways of measuring this. Well, usually what I actually care about is p bar, right? And so I want to know if p bar is a good estimate of the mean. Okay, but all I care about is if I sample, if they have the same, so is p bar a good estimate of x? Okay? And so I know, so in some ways, like, I already know this. I know the expected value of x bar is exactly for the expected value I want, which is great. But that doesn't tell me if p bar is a good estimate here. It doesn't tell me if p bar is a good estimate. That's the data I actually get. Okay? And I can also say that the probability that p bar equals the expected value of x. If this is let's say if it's drawn from a uniform distribution, what is this probability?
Just to step back, like what is the difference between the expected value of x and the expected value of x bar?
X bar. Yeah, so x bar is the average, is x, each x is a random variable, right? This could be xi instead here. And x bar is a random variable, is the sum of n random variables, right? So that's analyzing the random variable of this process, representing what this process will be, right? So I can short circuit, kind of, I can say x bar is here, and then this p hat is a realization of, or p bar is a realization of x bar. So it's one sample from this distribution. So if I have a very narrow distribution because I've averaged 100 or a million different things, that the sample I get is from this narrow distribution, right? Whereas the original x is from the uniform distribution, right? So this is, if I draw a uniform between 0 and 100, this is very unlikely to be 99. And it's very likely to be between 49 and 51. Right? Whereas a single pi, is as likely to be 99 as it is to be 51. But their expected value is the same. The expected value of them is the same because it's equally likely to be 99 and also 1, same like as 51 and 49. So they're balanced around the mean, but they could be a lot further from it. Okay. Okay, so again, what is the probability that p bar is equal to the expected value?
I mean, since it's a continuous distribution like this, it does end up being 0, right? If it's exactly equal.
Yeah, it's 0, right? So this is not helpful either. Okay, so saying that this doesn't tell me that much about p bar itself, it's useful that it's the right expected value, I know it's not going to be exactly the right expected value. So how do I quantify this? And so the concept of how to quantify it, which is used throughout all of data mining and machine learning, is kind of the default way, is called probably approximately so correct. Okay, and a bound like the one we're going to write is what would be called a so someone just called it PAC. Probably approximately correct. I can't just look at this. I need to write down. So I need to speak about the distribution of x bar, and I'm going to write down the probability that I'm going to say the probability that x bar minus the kind of the difference, the absolute value between x bar and its expected value of x is less than or equal to, let's say, is greater or equal than some epsilon is less than or equal to some delta. Okay, and so this guy is going to be an error tolerance, and this will be a probability of so it's probably a failure. Okay, so I'm going to say I want these to have the same. So how far is it going to be from the mean? Let's say e to the x is right here. And so the probability allows me to go some epsilon in either direction. Which curve is it? The blue one? Okay, so I go the blue curve, right? And so, and I want to integrate this blue curve. I want to do 1 minus this integral. So that's the probability I'm outside of here is the probability of failure.
Yeah. I'm a little confused at the difference between x bar and e of x in the probability. Is e of x as measured in some p bar, or
this is a constant. Okay, so e of x is a constant. It's a fixed quantity. In the central limit theorem, this is effectively like a known to give it's 50. right? It's 50 in our example. This is a constant. This is a random variable, right? Yeah, so this is, it's a little tricky, right? We're used to these simple random variables, uniform distribution. X bar is a random variable, and we want to understand this random variable.
We're doing all this guessing because we don't know what that is. So we can
Right.
then figure out that.
Yeah, that's correct. Sometimes we know a lot about f. Maybe we know f exactly, but the central limit theorem to say what x bar, the probability density function of x bar, might be really messy, right? So this is really all we care about. We want to know the probability it falls outside of this range, this safe range. So we set some error tolerance by some epsilon parameter, and then we want to say, what's the probability it falls outside this error tolerance delta? Okay, so you can't write it down without these two quantities. It depends on both of these quantities. You know, so if you, for instance, like in, you know, this comes up in other places as well, where you need these two quantities. In a lot of biological sciences, they rely on these p-values. Well, it's a bad example. One of the quantities is usually buried inside someplace else. Okay, so, but in order to do this correctly, you can't just say, it's not all, I can't set an error tolerance where it's always going to be in there. With the uniform distribution, if I say, I want to know some region where the probability distribution always lies in this region. Well, no matter what n is, that's always going to be between 0 and 100. If I start with that uniform distribution between 0 and 100. Right, so that's not going to help. If I say it must always lie in this tolerance. Right, so I need to set some probability of failure. You can think of this as like, maybe I allow 5% or 1% probability of failure, and I want to set some error tolerance. Right, and in this case, the probability of failure is an integral about here and here, and this might be like 40% of the integral, 30 to 40%. Right, so this area here, the sum of these two is delta, right? Is this area under the curve outside of this safe region. Okay, and so how is the blue one and the black one different? Well, the black one is more concentrated in this way. It has much less area, maybe half the area outside of this epsilon error tolerance. Right, so if I set epsilon this way, I can solve for delta, or maybe I set delta at being 5% and I solve for epsilon. And usually you can go one way or the other, or you can set epsilon and delta at certain values, and then you can solve for, well, how many samples do I need? How many runs of my algorithm do I need to predict something to get a bound for, say, one difference? Epsilon is 1 and delta is 0.05. And I can solve for how big n does n need to be. These are the sort of kind of trade-offs that will be fun. Yeah.
I guess at this unknown, how do we even get to that point? Because don't we have to take samples from some x, which is drawn from f?
Yeah, so we usually need to know something about f, and the question is, how much do you know? We'll talk about 3 different theorems that you can apply in order to do this on Wednesday. In the first one, all we need to know is that f is, we need to know its expected value and that it's always positive. Okay, in the second one, we need to know the expected value and the variance. And then the third one, we'll need to know the expected value and some absolute upper and lower bound. And it turns out these they get more and more powerful. They get, you get a more and more refined notion of this probability that you can use. So we'll walk through those and do some simple examples of those. But they're pretty easy. They'll end up being pretty easy to use. They'll just be simple formulas that you can plug in and you'll get a bound that looks kind of like this. I don't want to go into them today. That's probably too much. And I'll reintroduce this again on Wednesday. Okay, but typically everything is kind of connected around the idea of we're going to estimate the mean. The mean ends up being the thing that minimizes the sum of the squared errors. There's a normal distribution. If you have a noise model that's normal noise, it comes back to the right way to estimate the data is the mean, right? So all these things are kind of connected. They're very convenient mathematically, and they tie into each other. And so most of the models that we'll be looking at later in the semester, we're going to calculate estimates of quantities, which are going to be things like the means of data. Okay, in regression, where we're fitting a line, we're going to be something where we're effectively finding the mean, but only in the y direction. When we're doing clustering, we're going to find centers of different data sets, and the representation is going to be the multidimensional mean of these things. Okay, so estimating the mean might seem limited in how far are we from the mean, but it turns out it captures a lot of the interesting quantities that are needed to understand these actual algorithms used in data analysis as well. All right, so any other questions about this for today? Okay, so, yeah.
So that blue part else is 1 minus the blue part.
Yeah, so 1 minus the blue part is also equal to delta. Delta is 1 minus the parts in here. Delta is also the part out here. The whole thing integrates to 1. So if I subtract out the safe area, I get the bad area. Okay, so don't forget the homework's due at 2:45 on Wednesday, and I'll see you in class afterwards.